Right. Thank you so much for joining us today, Tomas. I'm excited to hear about Async IO. And after you're done with a few slides, we'll start on the Q&A portion.
Okay, so I assume everyone sees like my slides, I guess.
Yeah, it looks good.
Yeah. So um, hello, I'm Tomas Vondra. I work for Microsoft, and I'm working in the team that actually is responsible for like developing most of the Async.io stuff. And I'm involved mostly through working on the index prefetching, which is like related to this, right? So how I structured this is that I will try to briefly explain why we want to do Async.io, like what are the goals of the project. I will very briefly explain like how it actually works, like very high level overview and how you configure that. And I will share a couple couple numbers from like benchmarks I've been just doing as part of the development to give you an idea what kind of benefit in terms of performance to actually expect from that. And at the end, well, I don't know if the slides will be like 15 minutes or something, but after that, we will have a Q&A. I did get a couple of questions from Elizabeth, so I did copy them on the last slide, and we can go through that or we can discuss any other questions you have. Um, So, first of all, this is going to be like, I'm not going to go into very deep technical details of like looking at the code or anything like that. I assume this session is mostly for like people who are new to Postgres or like are not like intimately familiar with the code or AIO and that kind of stuff. So I want to give you more like high level overview. But if you want like much more details, there are a couple talks, mostly by Andres, where he talks about like the design, and also uh, you can see that there are like two talks from PGConf EU from 2023 and 2025, where he talks about like different plans for AIO over the years. And he also talks about like what went wrong with AIO, like what things didn't work um, in the development process, right? Like why it took so long, and because this is like a multi-year project at this point. So I think that's also very interesting because people are used to present like the sunny story about like everything like works and like the performance is amazing and all of that. But here he also talks about like the challenges of the development process and actually uh, getting things done, uh, which is great. So first, like, why do we want like async IO in general? So let's talk about like IO bound systems, right? Like if your system is not IO bound, isn't doing like a significant amount of IO and is like limited by CPU or maybe like network bandwidth or something like that, then async IO is like not very interesting for you, right? At least for, because we are going to talk about async IO in terms of like disk, like storage systems. Um, and for a long time, Postgres used to do just like synchronous IO. You essentially read a block from a table, for example, from a sequential scan of a table, you read the block, you process the block, um, you maybe return some of the tuples to the user, and then you read the next block and you process the next block and so on, right? Which, however, means that you have to wait for the I/O because you only initiate the I/O when you actually need the next block, right? So you initialize the I/O and then you wait. right? And it can take like, I don't know, on a spinning drives, it was like terrible, right? Um, you could be waiting for like 10 milliseconds for 8 kilobytes, and then you process that in like 1 millisecond because CPU is fast. And then you had to wait another 10 milliseconds for the next block, right? So essentially, it was significant performance bottleneck. And it also means that you can't actually utilize the storage capabilities because while you are working on the CPU, you are not actually like requesting any more data from the storage in the background, right? It's not exactly true. Like Postgres actually did a little bit of asynchronous I/O, either explicitly by doing PostgreSQL advice, which is essentially an instruction for the kernel to prefetch some of the data into the kernel page cache, or kind of like implicitly by relying on stuff like kernel read ahead, right? So for example, when we do sequential scans, the kernel would detect this pattern and would realize that like we have requested blocks 1, 2, 3. Surely the database will ask for block like 4 next, right? So it actually reads that ahead, um, and then we don't actually need to wait for the uh, for the I/O. But that only works for very simple patterns, right? It doesn't work as soon as you can't actually predict the the future blocks. This doesn't work. So anything like index scans or something like that, it's not possible to actually handle in this same way, right? At the operating system level. It needs to be done by the database. And I also mentioned like spinning drives, but like this can be an issue. Like only doing synchronous I/O can be an issue on current systems that are using actually SSDs because to actually use and saturate the SSD, you actually need to generate a lot of like concurrent I/O requests. Uh, you need sufficiently deep queue of I/O uh, to utilize the SSD. And similarly for like network attached storage on like cloud environments, um, those tend to have like a fairly high latency, at least compared to the local disks. And then obviously, like if you can request the I/O ahead, you may not actually need to pay the latency when you are actually waiting for the I/O, right? When you actually need a block. So this is why asynchronous I/O is uh, is important and why people started working on that, right? By issuing the I/O requests ahead, like you are scanning an index and you know which parts of the uh, table you will need because you know what's in the index. You can look ahead in the index a little bit. Then you could actually request some of uh, the pages ahead, and then not to actually pay the cost of the random I/O when processing the blocks, right? The other reason is that um, some of the other existing solutions, like the POSIX fadvice or even the kernel read ahead, they only work with buffered I/O, right? And there are reasons why people want to use direct I/O. And in that case, like these things do not work, right? You actually need to prefetch data directly into shared buffers, which means that the database needs to be more like in control of that. The operating system can't do that. And the database is the only part of the system that actually knows what data or is in position to actually predict which data may be needed next. So I think this is probably like even more important um, to make the database like smarter, right? So these are the why. Why do we want actually async IO? it gives the database like more control over the I/O utilization, and it also allows the database to like issue I/O requests ahead, right? So that it doesn't have to wait later when processing the data. So there definitely are existing AIO libraries and like different types of AIO libraries, but none of them is really a great fit, right? Like we couldn't actually use any of those because either it's very limited platform support, like Postgres supports like Linux, FreeBSD, Windows, and all of that. And we want to support the asynchronous I/O on as many platforms as possible, right? Ideally, we would support AIO on all of them. And then like each library tends to support only a small subset of like cases. So some libraries only work with buffered I/O. Some libraries only work with direct I/O and that kind of stuff. So Postgres actually implemented like two versions of AIO. One is completely custom implementation, custom framework, which is based on worker processes. And then um, and that's kind of the default now, right? Like because it works everywhere. And then we also support IOU ring, which is like a great modern framework for AIO, but unfortunately it's Linux only at the moment. So um, that only works on Linux systems, which probably is like most production systems are on Linux, but even then it's somehow limited, right? I will get to that. I think it's possible that more AIO subsystems will be added in the future. It's definitely like extensible, not user extensible, but it's it's a module, right? So you can add a new implementation. It's possible. Um, so it didn't happen at once, right? Like we didn't get AIO support in one version, but it was incremental. Like Postgres 17 actually added some infrastructure. Not actually the asynchronous thing, but it introduced some abstractions and like streamifications, we call it, like introducing the concept of a read stream. But it's still actually under the hood, it was like synchronous I/O with POSIX fadvice, which was used before. And in Postgres 18, a couple of months ago, actually introduced the real AIO, right? And it actually implemented AIO in sequential scans, bitmap scans, um, a number of maintenance operations like vacuums, pre-warm, auto pre-warm, and all of that. Uh, Postgres 19, which is expected to be released in a couple months, in like September this year, introduced a number of additional improvements, like improvements of the heuristics built into the AIO. It actually auto-tunes the number of workers. There is better support to actually show information about AIO in Explain. And then Postgres 20 hopefully will have also prefetching or AIO support in index scans, which is the only major type of a scan which doesn't actually have AIO at the moment. And that's the feature that I'm working on, right? So I can definitely answer some questions about that. We've been hoping to get index prefetching into Postgres 19, but unfortunately, it just didn't make it before the feature freeze. So how do you actually configure that? Like, so I mentioned that there are two different AIO variants in Postgres, and you can like choose one of those. And that is done by a configuration parameter called IO underscore method. And the default at the moment is like IO method worker, which means that you do have the backends, and those are the processes handling connections, and that's very traditional in Postgres, right? But let's say these processes are when they need actually to read data from a table or from the index or something, they don't do that like on their own, but they actually submit a request into a submission queue, which here is like a circle because it's like a circle queue, right? Implemented as like a limited space uh, for submitting requests. And those requests are picked by a pool of workers. On the slide, there are like two. And those workers are actually doing the actual I/O, right? So they will get a request from the I/O queue, uh, read that from the disk, put the result into shared buffers. This actually reads data into shared buffers, not just into the page cache as POSIX have advised. And then will notify the backend, right? And the backend will know that actually the data is in shared buffers. So this works everywhere. It's based on the same concept of like a background worker that we have in Postgres for many years now. Like we do have background workers for things like logical application and even like parallel workers are this kind of workers and that kind of stuff. So the how do you configure that? Like the size of the pool is configurable. In Postgres 18, like in all versions, you can have 1 to 32 workers, right? So at most, you can have like 32 workers. In 18, the default number was 3, which I think is like very conservative. It's very low. In 19, it was actually changed to or improved to auto-tune to increase and decrease the number of workers as needed. And the default like limits are 2 and 8, right? So if your system is going to do a lot of I/O and all the workers will be utilized all the time, then it will gradually actually increase the number of workers up to 8. And you can, of course, like change these things, but it requires a restart, I think. So this works great, but it also has a couple like issues, right? Or limitations. So first, like the workers are still doing synchronous I/O, which means that if you have 32 workers, which is the maximum number, then you can only have like 32 I/Os in flight through this. Um, if the queue is like full and the backends can't actually fill additional or submit additional requests, they will actually fall back to doing like the I/O on their own, right? So if you have like a super busy systems with many connections, actually the backends can actually do a lot of I/O on their own and kind of like saturate the storage that way. The other thing is that the workers and the backends need to communicate in some way, right? Like the backend will submit a request, and then it needs to notify the workers that there is a new request, right? And then when the worker completes the I/O, it needs to submit, like notify the backend that may be working, may be waiting for the I/O. And this happens through signal, and there's like a limited number of signals that you can send per second, right? Which uh, I think it's like a 4 gigabytes per second if you translate that uh, into like bandwidth that a single worker or single backend can actually do, right? So if you have like many backends and many workers, it could be a multiple of that, but there is some amount of like overhead. Um, in the other method that we Postgres supports is IOU ring, which is like a very modern framework to do IO asynchronously in a process. And there are no workers in this case, and each backend is essentially issuing and managing their own IO. And it's done that by the library IOU ring, which means that each backend has essentially like two queues, circle queues, similarly to before, for communicating with the kernel. And one is for submitting the request, and the other one is for like completion, which means that the kernel completes the request and notifies the worker by uh, adding stuff into this completion queue, right? Which means that like each backend is going to handle its own IOs. There is no central queue that could be a contention point. And the other advantage of IO ring is that it allows like kind of like massive depths of the IO queues, right? Before with the IO method worker, we've been limited to like one IO, one in-flight IO per worker. With IOU ring, you can have like hundreds of IOs uh, per backend, essentially. What is not so good, of course, is that it's not available on other platforms. Like it's a Linux-only thing. And also, there have been some security issues with IOU ring in the past, uh, which resulted in it being disabled in Docker and various other environments. So uh, if you are running stuff in Docker, for example, like in containers, um, you may not have the option to actually use IO ring, even if you are on Linux, right? The other thing that I didn't kind of like explain is that IO ring happens in each backend, which means that certain things can't actually be offloaded to the workers, right? So for example, in the worker, like here, if you need actually to read data from a disk and you do have data checksums enabled, then the checksum verification will be done by the IO worker, not by your backend. And that can be um, quite a bit of CPU, right? And Postgres 18 actually does have data checksums enabled by default. So uh, in this case, it's kind of like offloaded and even possibly paralyzed. With the IO method uring, um, that's not the case, right? Like the backend is actually handling the IO on its own, and therefore it will pay the full price for all of this. And also, there's like for IO method IOU ring, there's not a lot of like configuration parameters, right? Like you just say like IOU ring and you don't need to configure any size of the worker pool or anything like that. We still do support like a third method, which is the IO method sync, which essentially means like do synchronous IO with the PostgreSQL device for like prefetching. Um, it still goes to the new infrastructure, but as um, it's kind of like a defensive thing, right? Like we want to have something to fall back if there is like a bug or something, right? But other than that, I don't think there is like a reason to actually use sync in on current systems, right? Um, could you invent a new method? Probably I haven't tried, but for example, I've been thinking about like combining worker and IOU ring. So that you can actually have worker and you don't actually you can offload some of the stuff to the workers, but also you are not limited by the number uh, uh, of workers, like the IO queue depth, right? So I think this should be possible, but I haven't tried, and I don't even know if this actually makes sense in the end, right? But I think it's feasible. So how do you actually monitor uh, AIO? Let's say you have enabled like one of the IO methods, like um, a worker or something, and how do you actually monitor what's happening? So you still have all the wait events and all of that. So you can actually use that, and you can use all the statistics the system provided before, right? And of course, you can still monitor the system level I/O statistics, right? Like provided by the kernel. But we also have like a new system view, which is called PG AIOs, and that's actually the listing of the currently in progress AIO IO requests. And in this case, like in this example, I'm showing you like when there is like a query running in index scan with prefetching enabled, right? So all these IO requests are actually coming from a single PID from a single backend. Then there is like an ID of the IO request. There's something called IO generation and all of that. But you can also see uh, length of the IO request, like how much data was requested, if we managed to kind of like combine multiple reads into a single one. Um, you can see some results, like if it actually succeeded and all of that. So this is useful because it allows you to see which backends are generating IOs, for example, right? So you could do some grouping on the PID, or maybe you could also join this to pgstat activity and all of that. I think it's more for like a developers than for regular users, but this is probably the best way to kind of like get an idea which processes are uh, which backends are generating I/O. Okay, so this was like how AIO, how to use AIO essentially, and now some numbers, right? I think that like I'm doing a lot of benchmarking as part of the work, and I think like benchmarking in general is kind of like tricky, right? Because I can definitely invent workloads that are like showing infinite improvements, right? And I don't want to do that. So I will show you some results that I think are like reasonable, and actually you could observe that in production. But also this is like very workload and hardware specific, right? So if you have a system which is serving most of the queries from cache, then this doesn't really matter, right? Like it could be either from share buffers or from page cache. AIO will do very little for you. Uh, but I will show you some queries that don't have this, that are actually doing a significant amount of actually physical I/O. As I mentioned, sequential scans and bitmap scans did already have some sort of asynchronous behavior before, but they still do see some modest speed ups with AIO, right? Since Postgres 17 and so on, there are some improvements, like up to 2x. And that's mostly thanks to combining uh, larger requests into a single IO. Gives you better efficiency or offloading checksums, and even just like better control over the prefetching, so that actually we are prefetching when the operating system couldn't actually do that. And then index scans, which unfortunately at this point are not going to happen in Postgres 19, but you will have to wait at least like a year, uh, maybe a year and a half to actually get that. And those um, do not actually have um, any asynchronous behavior right now, which is a bit weird because like um, index scans are the main source of random I/O in Postgres databases, right? Like indexes generate random I/O. And those can actually see huge speedups uh, with prefetching, with AIO providing prefetching. And it's easy to demonstrate like plausible uh, cases with an order or two orders of magnitude speedups. So first, this is like a result from a sequential scan, like a timing. Um, you can see different versions of Postgres, like 16 is before any AIO was introduced. 17 is where like the streamification, like the preparation of infrastructure happened. 18 is where the actually true AIO was introduced. 19 is what will be released in a couple months. And prefetch is like essentially 19 with the index prefetching. Um, so I included that because of index scans, but it doesn't make sense for sequential scans. And on the y-axis, there is always like a duration in milliseconds for all the charts that I'm going to show you. And you can see that like on 16, it took like close to 4 seconds. And then we are like gradually improving up to like less, well, about half of that, like which is the 2x speed up that I mentioned before on 19, right? So I think this is very good, especially considering this is actually leveraging the kernel read ahead, right? So this was actually doing the some asynchronous I/O before, right? So and this is, by the way, this is on my local machine that I use for prefetch for benchmarking all kinds of stuff, and it's using the IOU ring. But with Worker, it would be about the same, right? Like I didn't see any significant like differences between those two, at least on these benchmarks. With bitmap scans, which means like reading a bitmap, reading an index into a bitmap, and then processing the bitmap. You can see that like between 16 and 17, there was like very little difference. And then on 18, there was a significant speed up, right? And that is because the prefetching in the bitmap scans got like much more accurate, right? And also it's actually driven by heuristics in Postgres itself, right? So it's not relying actually on the kernel read ahead. And since then, like in 19, there's a little bit of improvement, but it's also like very small difference. So it could be like run to run variation in this case, right? For index scans, um, there's like no asynchronous IO even in 19. There is a little bit of improvement between 18 and 19, but that's mostly, I think, like efficiency or improvements in other parts of Postgres, right? Not in actually doing the I/O. But it still takes like a second, right, to do this particle index scan. But with the prefetching, which we could do in Postgres 20, hopefully, it's like an order magnitude faster, right? Like maybe even faster in this case. So that's something I'm looking forward to, right? The I did similar like benchmarks on because this is with like local NVMe SSD, which can do like 20 gigabytes per second. So it's quite powerful storage system. But I also did that on like a cloud environment with similar results, right? Like similar uh, behavior. So you can see that for sequential scans, we did get a lot of benefit in 18. Since then, there is like small run-to-run variation, like no major improvements. For bitmap scans, it's kind of like not much difference. I think this is more like run-to-run variation. I think in this case the prefetching that we already had before was doing a pretty good job. And for index scans, again, like uh, this is a remote SSD-backed storage, so it's still I would count it as like high latency, but it can actually handle a lot of like requests concurrently, right? So if you actually can issue requests ahead, you can get order of magnitude speedups, maybe even more, right? So I think this can be quite beneficial for a lot of systems. So this was what I had prepared, right, for this session. So I do have a slide with questions that I got uh, before the session started, but maybe someone already has like other questions that I could answer.
Thanks, Thomas. Yeah, maybe we'll take some questions live first, and then we can switch to the pre-submitted questions. I know the first pre-submitted question came in pretty early, so maybe start there, and then while Thomas is answering that, if anybody has questions, throw them in the chat, or I'll let you come off mute in a second. So yeah, go ahead, Thomas. Start with that first question.
Right. So the first question, I think I at least partially answered that during the session. Like, are there any realistic scenarios where IO method sync would be a better idea than worker or IOU ring? And I frankly I can't think of any. Like we use that as like something uh, as a fallback in case there's like a fatal bug, so that people can actually switch to something that actually works.
Ahora es que me dan.
And right, other than that, I haven't actually used like sync.
Claro, yo creo que no pagan.
Okay.
Sorry about that. Someone popped off mute. I think I got it done.
Yeah. I don't think there is like a realistic scenario where sync would work better than the other methods, right? Like,
Thanks.
so yeah.
That's helpful. If anyone wants to come off mute and ask their question, I'll give you a couple of seconds to do that. All right, sounds like people are feeling quiet today. No worries. Um, Thomas, if you want to pick a question, you don't have to go in the order, but we're welcome to answer those. And then if anyone has a question while Thomas goes through the rest of it, feel free to throw that in the chat.
I think it's easier if I just go through the
Okay,
questions one by
sure.
one. Of course, like if anyone has a question after the session, feel free to just drop me an email or something, or ping me on Discord or whatever. I'm happy to have a chat. But let's go back to the questions. So when would customers on RDS or like other hosted platforms see a performance change? So I think I showed that actually on the second set of uh, charts. Those were from like a regular uh, Azure instance, right? With and I assume that the same thing would apply to Amazon or any other cloud provider with like network attached storage. And even if you happen to use like a local storage on the instance, like NVMEs, those would also benefit from this because the first set of charts was actually from my local machine running that kind of storage. Uh, so I think it's very general improvement, right? Like it doesn't require any special hardware. Like if you have hardware that requires, or like storage hardware that requires either like um, deep I/O queues, like many um, concurrent I/O requests to actually saturate and leverage the capabilities of this, which is like NVMe drives, for example, you will benefit from this. Um, if you have a storage that has like high latency, like network attached storage in cloud environments, you will also benefit from that, right? Because you will not have to pay the full price of the latency later. Um, so
Tomas,
how
it
can
looks
I?
like I was just gonna say it looks like somebody had a question in the chat about AIO and random page cost, which is funny
Hmm.
because you were just saying that you did a talk for Posette about random page cost. But that's a good question too. Like, are those things kind of interacting with each other in some way?
I think that's an excellent question. And we are actually, I think all the changes um, in Postgres in prefetching, kind of like in the past, like AIO, and but also before that, kind of neglected adjusting the cost model to account for prefetching, or like uh, the bitmap heap scans, for example, completely ignore if you are uh, enabled prefetching or not. So I think we will need to do something about that, right? Like so that we actually do know uh, that, for example, an index scan is going to benefit from prefetching. If it's going to be done by adjusting random page cost, I don't think so. I think it will be by actually adjusting the random, sorry, the cost model itself, right? Because the cost of a random I/O didn't actually fundamentally change because of this. It's more about how we actually issue the I/O, right? So I don't think you should actually change like random page cost just because you are using AIO.
Got it. Thanks.
Okay, so how can I tune Async IO? Well, there is not much you can tune, to be honest. You can choose the IO method, right? I would, I kind of prefer the IO ring because it's like more modern and uh, allows more in-flight IO requests without actually having to configure the workers. But in practice, I don't think you will see like a significant difference, right? And if you are using IO workers, then you may need to actually increase the limits, especially on larger systems. You may need like more than 8 workers quite easily. But if that actually is not enough, the system will just, fall back to doing the I/O in each individual backend, right? Um,
I'll read the question here that just came in. I'm
mm,
running Postgres 17 on a Ubuntu laptop. My database contains a table with more than 18 million metadata records. When I query the database through Django application and search for book title, it takes 30 seconds or more. I've enabled the PG trigram extension and created a gen index. I'm running a following, basically a select ID and title where book is like. However, the query is very slow despite the trigram index. What could be causing this, and how could I improve the performance?
mm. So,
Yeah, well, I guess one note for this question is that most of the async IO stuff is on Postgres version 18 plus, right?
mm, right,
Um,
but I think that's also um, what is being used, right? Um, or which Postgres? Oh, it's 17. So it actually can't actually leverage the AIO at all. So it's kind of like unrelated. But also it's likely an index scan, which doesn't have like AIO in any of the versions, not even in 19, which is going to be released in September. So um, it's actually not related to the topic of this talk. I'm willing to take a look. Like if you send me an email, I can give you some advice. But you can also like ask about this on one of the developer mailing lists or like PGSQL performance or something. And I think people will help you with that. It's not very clear to me like what exactly is the expensive thing on the query, right? So I don't know. So my email is tomas@vondra.me. That's just answering the question from the chat.
Yeah, and I'll for folks in the chat also just mention that there's a Postgres community Slack channel where there's quite a few people answering questions. And then there's a fairly active Reddit thread for PostgreSQL that's well monitored and several community members answer
Yeah,
questions like this for production. So I'll drop both of those links in. But yeah, one of the
right.
questions before we kind of run out of time that I had for you, Thomas, is, and I know this is probably a longer conversation, so
Mm,
we can try and keep it brief, but I'm curious what kind of like benchmarking
mm,
tools you're using to benchmark any performance with Postgres. Like, are you
mm,
mostly using kind of a PG bench thing or just some kind of standard Postgres tool? Or I assume the
mm,
Microsoft team has a pretty advanced performance testing suite, since you guys are doing a lot of this kind of heavy performance work on Postgres. But yeah,
mm.
you don't have to give me a 20-minute answer, but I'm curious how kind of what your recommendations are for performance testing.
Right. So I think the answer is that I'm using pgbench like quite often or like regularly, but more as a way to drive the benchmark. I'm not actually using the built-in pgbench, at least not like regularly, right? But I'm actually developing like custom scripts um, because during development, I'm actually more focused on like very specific cases. So I generate like a data set that I think is important, and then a specific query to actually and measure that, right? So when people say like pgbench, I think they mostly talk about the built-in TPCB like workload, and I don't think that's very useful, at least not for my use case. But of course, like I also use the well-known, like widely used, like benchmarks, like for TPCH, for like analytics and so on. But that's mostly when I need to publish like a result or like share, like present something to other people, right? But most of my development work is about actually very simple custom scripts that are say like generating table that is like perfectly random, right? And doing some queries on that, or then generating a table which is like perfectly correlated and doing some measurements on that with specific queries, right? So that's it.
Cool, thank you. Yeah, I mean, I would be interested in that as a testing repo. Like if you get bored later and you want to open source
Mhm.
your testing scripts, I think that would be useful for other folks in the community.
Yeah. Unfortunately, like all my scripts are awful, and they are also like very tightly tied to what exactly I'm developing at that moment, right? So it, it's very, very close related to whatever patch I'm working on at the moment. I usually do post them to hackers to the mailing list along with the results.
Oh, nice. Cool.
So that usually gives you a little bit of context, like about like the purpose of the test, right?
Yeah, it's awesome. We'll kind of, I'll leave this open for just one more minute for
Mm.
a last question. But I think, Thomas, you kind of covered the future versions in your slides, so I think we covered that.
I think I see there like one more thing that I forgot to mention.
Sure.
There's like, is there any particular workload, query heavy, write heavy, or whatever, um, that will. One thing I didn't mention is that all the AIO in Postgres at the moment is for read-only stuff, right? We do not actually use AIO for any writes. So, for example, um, we do use AIO in vacuum, but we only use that to actually read the data from the table or like from indexes or whatever. But then the writes are actually still going to the usual kind of like synchronous uh, thing.
And
They don't go through the stream.
right. And so you can be IO bound on writes because everything that writes has to go to the disk. So
Yeah.
is there a future world in which we're doing asynchronous writes and reads?
Yes.
Okay.
I do think that like definitely something Andres plans to do, but it's just like more like complicated, I think. So it needs to be incremental development.
Well, awesome. Thank you so much. I'm gonna pause the recording